to move away from these kind of examples, if you like, we have to put together a system with advection and also time dependence. That is almost but not quite geostrophic. Okay, so what we're going to do is separate the flow into the geostrophic part and the ageostrophic part. Okay? And we'll say that the ageostrophic part is a small perturbation. Right? So that is the approach. So we'll start with the shallow water momentum equations again. And this is the complete shallow water momentum equations. And this is the substantial derivative operator, so d by dt plus advection. Okay. And so let's just ask the question, what would happen if we just assumed the flow was geostrophic and we substituted it into these equations? So let's just say that ug is g over f dh by dx, vg likewise, and we just put that into these equations, right? And we'd also have to put it into the definition of the substantial derivative. So our d by dt would become dg by dt, okay, so which is d by dt plus advection with the geostrophic flow, right? Now, we can put the geostrophic values into the advection part. What if we also put it into the Coriolis part? So instead of using the full flow to calculate the Coriolis force, we use the geostrophic flow. Well, then you get this equation, dg by dt of ug minus fvg is equal to, plus pressure gradient force is equal to 0. So what's wrong with that? So it's pretty obvious that's not going to get us anywhere, because obviously this is geostrophic balance, which means that these two terms, by definition, will cancel and your tendency will be 0. Okay? So all we've done is recreate geostrophic balance, which is obviously what was going to happen because we set out by assuming geostrophic balance. Okay? So we have to back off a bit from that position if we're going to find something useful. So instead, we'll just say, how about if we make sure that the equation is linear in the small ageostrophic part? Okay? So if this is the sort of usefulness of linear analysis. If you have something that is small and you have an equation with linear terms and nonlinear terms, then the nonlinear terms in the small thing are going to be negligible, right? Because they're going to be squares, etc., of those small things, which are very small. So if we make sure our equation is linear in this, then that'll be useful, right? Because we can neglect the nonlinear terms. And linear equations are easier to solve, right? So in order to do this, we'll use the full flow, v and u, in the Coriolis terms, but we'll still advect with the geostrophic flow. Okay? So what are the consequences of doing that? Right, so let's just put that in. Here's our sort of quasi-geostrophic momentum equations. So we've got geostrophy in the nonlinear and tendency terms, but we've kept the full flow in the Coriolis terms, right? Let's form the vorticity equation with these momentum equations. So as usual, we cross-differentiate, we eliminate pressure gradient terms, and we end up with an equation for the development of the vorticity. And it's the development of the geostrophic vorticity, so d by dt of the relative vorticity plus these advection terms plus relative vorticity now times the divergence. Now this is important. The divergence of the geostrophic flow is 0. At the moment, because we have assumed that the flow is on an F plane, right? We have not admitted any variations in F in our equation set. And so the geostrophic flow on an F plane, you can say that H is a stream function for U and V. So U and V are non-divergent, right? H is just that the pressure is a stream function for the geostrophic flow, but only on an F plane. If you start to let F vary, then you will find that there is a divergent part to the geostrophic flow. We'll deal with that next, but for the moment, we can cross this term out, cross that term out because we're not allowing F to vary. And so because of this, we end up with an equation for vorticity, which should be fairly familiar. It looks very much like what we had last week. The geostrophic tendency of the absolute vorticity is given by the divergence of the ageostrophic flow. So the divergence of the full flow, which is not 0. Okay? How about the continuity equation? Because we need that as well. We need not just the vorticity equation, but also the continuity equation. And so here's the continuity equation in the form of the flux of layer thickness, h. So d by dt of h is given by the flux of the layer thickness. And you can also write that as a substantial derivative of the layer thickness depends on h times the divergence, as we did last week. Right? So then that gives us, if you expand this term out, if we use the geostrophic flow, Vg dot grad h plus h grad dot v. Now, this is fine, Vg dot grad h, that's all right. But h grad dot v, that's a bit tricky, because it looks like a linear term, doesn't it, in v, because remember v contains the ageostrophic part, so the term needs to be linear in that. Trouble is, h also depends on v, right? Because h is a variable in the equation set. So if we got h times v, that could be nonlinear if it depends on the ageostrophic flow. So for consistency then, we must make an approximation here. We must say that our standard reference layer thickness, which is a constant, is big H, and our H is big H plus this delta H, which is the variation of the layer thickness, right? Now, so here it is, H is big H plus delta H, and we say that delta H is small, okay? And then we can linearize this term in the ageostrophic flow by just assuming for that term only, not for this term, because we need gradients in this term. But for this term, it's just a constant times the divergence of the ageostrophic flow. So that is a consequence of the assumptions we've made. We have to do this with the continuity equation. Now we have a continuity equation, which is the rate of change of this delta H, plus Vg dot gradient of that delta H plus H times the divergence. So we can write it like this. The substantial derivative of delta H is given by the divergence, right? Now, so in order to keep the ageostrophic term linear, we had to make a strong assumption in the end about the stratification, because what this is telling us here, this assumption, is that the stratification is essentially represented by the layer thickness. Can't vary in the horizontal. It can vary in the vertical. If you've got lots of layers, they can all be different thicknesses, but not in the horizontal. So that's a consequence of the assumptions we've made. So let's just rewrite the continuity equation that we just derived as this. F over big H d geostrophic by dt of delta H is given by F times the divergence. And this should remind you of last week that this is an isomorph of the vorticity equation. It's very similar. You have d by dt of the vorticity is given by F times the divergence, and also for the layer thickness is given by F times the divergence. So you can equate the two. You can equate those two divergence terms, which are the same, and say that the rate of change of this layer thickness is equal to the rate of change of vorticity. So vorticity is produced by changing the thickness of the layer. Okay? And you can then just take this term over to the other side and lump them together, and we have the conservation principle. Right? It's not quite the same as last week because we've got this linearization of the stratification, but here we have something that is conserved. Right? dg by dt, d geostrophic by dt of f plus xi plus f delta h over h is equal to 0. So that's conserved following the motion. Right? This is the conservation law for potential vorticity. It's just like last week, except it's not quite the same. It's quasi geostrophic potential vorticity. Right? So instead of being f plus xi divided by h, it's f plus xi plus another term. So it doesn't even have the same units as the potential vorticity we considered last week, which was the Ertl potential vorticity. But you can relate the two. So here's the Ertl potential vorticity. If we make that assumption about the stratification, h plus delta h to the minus 1, okay? So if we say delta h is small, then that gives us this. And then you can get out this term quasi-geostrophic potential vorticity. Using scaling arguments, that the Rossby number is small. This means that the term involving relative vorticity is small compared to f, and so we can neglect this term, and we'll recover the thing we deduced above, that the quasi-geostrophic potential vorticity is just equal to the absolute vorticity and another term which involves the layer thickness. Okay? So this linearization of the layer thickness is a surprising consequence of our insistence that the flow be close to geostrophic. And as I said, in a vertically continuous framework, it means the stratification is uniform in the horizontal.